I would like to speak about a method we tried out on the electromagnetic observation regarding the gravitational wave events with quite a lot of colleagues, and actually the whole inspiration was based on the Fermi's group paper, where they claimed that they have found some kind of signal with the September events. So we have seen similar pictures earlier, so I would just run through. This is the very first event. The only new information is that the redshift, we know the redshift of the event, and we can place it in the universe, not very far away or far away, depending on how far objects we are observing. You can see here a very nice figure with a fitted signal, but of course this one is not so nice. It is much more noisy, as we have seen earlier in the previous presentation. Here is the second transient, which was very weak, so they have not called it gravitational wave signal. Instead of, they called LIGO transient. And here you can see the redshift again. It's 0.2, so it is far away, or not so far away, regarding the other GRBs and similar transient sources, or compared with the galaxies, it's really far away. And let me remind you that here you can observe the UTC date of the observation. It's 10 minutes before 10. It's 5 minutes before, or 6 minutes before 10. And here's the third one, which was about 3:30 on Christmas Day. So it is not so problematic that we have observations only around 10 o'clock. But the latest one is quite strange, because it's about 12 minutes after 10. So you can wonder whether or not these events are somehow real or not. Of course, probably they are real, but there should be some kind of explanation. For example, the noise floor, why they have been observed in the morning hours and not later. Probably the noise will be the explanation. But what is more interesting is the signal, which is quite noisy too. So it would be very important to find some other companion of the gravitational wave observation, just to strengthen the statement that it is a real event. We have seen earlier that it is really noisy, and people are investigating the method, the natural filtering methods and other kind of methods, how it is working, because as you are considering the polar spectra only, you will lose information, and it means that you will enter into a nonlinear regime, and everyone knows that, at least who studied some signal processing, that you can find anything in the noise if you wish. So I think that these signals are real, but it would be really interesting to find electromagnetic counterparts. There is a very nice picture, just the imaging. The really interesting thing is that all the events observed so far are just above the typical values earlier thought to be possible as a gravitational wave signal. You know? This one is really a very fun thing, because earlier everyone calculated and simulated double neutron star or similar systems with total mass below 5 or so. So, you know, that, oops, sorry. There is a value of 60 solar masses as a final value. So it is not working as we think. I think that not all the theoretical statements are true. So it would be really interesting to investigate this argument. And the electromagnetic transient question is really a serious one, I think. And we have quite a lot of equipment in the sky to observe electromagnetic transients. We have the GRB satellites and different gamma detectors on the satellites and on the International Space Station. There are other missions working together in the interplanetary network, AGIS, and sometimes we have balloons which are observing the gamma emission from the sky. What we have used was the Fermi satellite, earlier called GLAST, but get the Fermi Nal after it was successfully launched and they got it working. And this satellite observes the sky. Here you can see the GV sky. It is a 2-year observation. And you can see that there are a lot of small sources, and sometimes they are changing. So the sky, the high energy sky is really a transient sky. So it is not like the every night optical sky we are observing. And it is really a problematic thing to observe the transients and to separate them. As I have told you that there are problems with the earlier calculations, and the people calculated GRBs as a possible sources of the gravitational waves with low masses, I think, that they are below 10 solar masses or so, total mass. But they were really a very nice simulations with all the magnetic field, and they have used supercomputers to calculate it, but the world is a bit different, or the masses are bigger. We know that the observed redshift is somewhere in the 0.2 range, and there is the redshift distribution of the GRBs with measured optical absorption or emission lines, so they are real optical redshifts. And you can see that we are speaking about this region for the gravitational wave sources. The GRBs are somewhere here in around 2 or 3, where the star formation somehow peaks. And the metallicity is not very high, it is under. So the question is that, is there any connection between the GRBs and the gravitational wave sources? I would not say that there is a sure connection. I think that some GRBs probably mislabeled as GRBs because they could be some kind of gravitational source signals, but quite a lot of GRBs doesn't have a measured redshift. So practically it is possible that the dark GRBs are somehow contaminated with the gravitational wave sources. And there is the sky distribution of the probability of this January event. And here you can see the GRB's distribution in the sky. And you can see here is the galaxy plane. This is a galactic coordinate system where the optical observation is really hard. There are some holes, but usually the density drops. Of course, you can measure the distances, measure the redshift, and you can try to find some groups of GRBs in the sky. We have found earlier 2 such kind of examples. There is a big mass, a big wall around z equal 2. And there is another very interesting structure around z equal 0.8. It's a ring, and you can see that it is really a strange thing. I would not say that it is an alien artifact, but somehow it's really a very strange think that the probability is very low that you will find such kind of thing. So somehow some induced star-forming behavior or similar thing can be behind this, if you ask about it. The Fermi detectors we are speaking about these detectors on the spacecraft. They are the GBM detectors, and here this huge detector is the LUT detector for the GV detection. The GPM detectors are consisting of natrium iodide crystals and photomultipliers plus 2 BGO crystals. And they are really a very fine equipment. We can see and we can observe every photons coming out, every observation coming out from these detectors with 2 microsecond resolution, and there are 128 energy channels for each detectors. So you can access those data on the NASA server, and we can simply download them and get the events. Of course, if you have a source, to get the count in the detector from a real physical emission, you have to use the detector response matrix. What is this? For example, here are 2 examples for the natrium iodide and the sodium iodide and the BGO detectors. You see that as the angle between the detector normal and the source is changing, you will see how the effective area is changing. And of course, the matrix which is converting the incoming mono energetic photon into counts will change too. We can download the detector response matrix, but this one is different for different directions. So practically, if you don't know the direction, you cannot use this matrix. Okay. How it is working on the GRBs, there are different kind of thresholds and different kind of energy channels, and they are measuring the background, and when the signal is above the background by 5 sigma, for example, the detection starts. Altogether, there are about 70 or 80 different kind of triggers in the computer at the same time, and any of them can trigger the detection. Okay, so here are the results of the Fermi group regarding the September 15/7. You can see that this light blue region is where they said that they have found the signal regarding the detection time of the gravitational wave. What they have done was nothing else, but they have chosen different direction on the sky, and they calculated the probability, the detector response matrix for each position, and they have summarized the counts and get this data. Okay, here are the high energy detectors results. What you can see is that you don't see anything strong. Okay, so it is very near to the noise. What is more interesting, that if you combine the data, you can get a really sharp peak, okay, just after the gravitational wave signal. So the question is that without the detector response matrices, can we do something similar without knowing any directional information? Only the time when the events happen is known for the observer, and the problem is to find a signal in this place. Here is energy spectra, and here is the... So what we have is energy ranges and detectors. And we have a count for every millisecond, for example. And we have a observation of the photons. We don't know the detector response matrix because we don't know the direction. The question is that how we can do any kind of analysis of such count data. The simple solution is just summarize everything. It is very simple. Everyone would do it in a laboratory practice at the university, right? This is the first thing what the people are doing. But here the problem is that all the detectors are not facing to the signal, are producing only noise. So adding noise and more noise to the signal will drop the level of the probability to find anything in the noisy part. So the question is that how can we separate out the energy channels and the detectors at the same time? The simplest thing is let's choose some kind of algorithm and do the work. It was really interesting that a very simple algorithm will work. Just give some weights for the energy channels and for the detectors, normalize them, and you can calculate from the intensity signals this kind of composite signal. This C signal is the count in a given detector and in a given energy channel. We can calculate the maximum of the signal within the search interval and outside the interval, and somehow maximize this ratio, the signal peak to background peak ratio. And this is the simplest way to find out the real weights. I will change the weights. The C is given, and this is what I maximize. We have given octave code using fmin search working with the MATLAB 2, which does that kind of things. Why it is interesting for the CPU or GPU point of view? It is because it is a matrix multiplication, and it is really interesting that it is not well suiting for the GPU environment. You can calculate the running time or the efficiency of it is not a very strong GPU. It is happening in my graphical card on my desktop computer, but it is pretty nice. And you can see that the gigaflops are raising, and there is a 100-fold raise when you just let more and more channel in the output region. The problem is that we have only one output channel. This 128 is around the same amount. How many detectors and channels do we have? So practically, you can see that we are here down in this region. And even using QW is not helping. Of course, the CPU is a bit slower if I'm using a Atlas optimized version. So just again, the value is 14 against 3. So it is not bad, so that we started to try out the code. The only problem is that we have a few hundred seconds multiplied by a 1 millisecond resolution count, which gives us almost a million point. And if you raise the value here, it's 500,000, we get about 9 gigaflops, and we get only 6.7 for the GPU. So it is really interesting that it is not worse to use GPU here. Of course, we would be able to somehow optimize the whole thing and so on, but it would be very problematic. It would take quite a lot of time. And I think that when the whole thing is within a factor of 2, it is not worth to play too much. So it was really a interesting equipment. This Plus and Atlas libraries just to try out. Okay, we have chosen the same kind of energy channels what the Fermi group have chosen, but these are quite typical, so other people are using the same things. We have only 80 time series. That is another problem with the GPU, that we are not able to fill all the blocks perfectly, so that is another problem. And there was another problem with the background. We used only a very short time, so simple polynomial background fitting was done. And here are some results. There is a GRB, there is a light curve, what we have observed. This is what the Fermi group produced in the quicklook data. You can see that it is much more detailed. It's noisy, of course, but it's a better time resolution. And we have found the same signal what the Fermi group have found, I think, for the September event. And we were able to find a weak signal for the October event, the LIGO transient. Here the probability is lower, it's about 97%, but this is the same probability what they claim to be an event, so it is not very surprising. We tried the Christmas event. You can see that it is nothing. Here you can see the background, and here you see the peak, which is not high enough to be claimed to be a signal. And there is the January event, and this one is not so bad, but the value here is pretty low too, so I would not claim it to be a real signal. It's just before the event by 50 milliseconds. There were other kind of searches in the electromagnetic observation. Nobody have found anything, and they have analyzed the Fermi data, but use only one detector data, or a few detector data gave them no signal. Okay, in the January case, it's interesting that they have found one peak just before the event above 1.4 MeV, and they have found an optical transient, but it is probably connected with a GRB on January 5th. So the big question is that, I would go here, is the real or not? Here the red points are the same day background of the September event, and what you can see is that there are some points regarded as a background somewhere in this region. This is the signal peak to background peak ratio, and this one is the softness. And here are the GRBs, here are the gravitational wave signals. So it's really noisy, and what I can say is that more observations are needed just to be sure whether or not there are real or not.
Thanks. Short questions? So just a comment, because this gravitational wave events were from black holes, right? So we don't expect really any electromagnetic radiation, right?
It's a really interesting question.
Yeah, and then the thing is that because the thing that we are detecting the black hole systems now and not neutron stars doesn't really mean that they are rarer than neutrons. That the neutron star systems are merging less frequently, but this is just the fact that the black hole systems have a larger chirp mass, so so the amplitude is larger, and we actually probe a larger volume. Basically, it may not mean necessarily that they are more frequent or less frequent. We just because 0.2 is 1 gigaparsec. In case of neutron stars, we reach maybe 8 megaparsecs. So you know, this is the volume frame.
Yeah, but we have more neutron stars.
We at least know 7 neutron star binary systems, right?
In
our
the
galaxy.
galaxy, yeah.
But this is a very interesting evolutionary problem, right? How often they merge and so on. Right? So
Yeah. No, my problem is that you know that I don't believe any theoretical things today. I used to, but I don't think it's real, you know, because earlier I really worked and just followed every such kind of simulation of merging neutron stars from the gamma ray burst point of view, and really very nice simulation have been calculated, and everyone tried to find any connection between gravitational wave signals and gamma ray bursts, and nobody was
short gamma ray bursts.
Short gamma ray
My
bursts.
question would be, those gamma ray bursts are short, all of them are short?
Short, yes.
Okay. Yes.
They are short gamma ray bursts. And, you know, so I would say that you have to anyway analyze your data, and you cannot miss that point because everything what had been told by the theoretician could be, you know, different.
Yeah,
So I'm not saying that they are speaking nonsenses, but I'm saying is that, you know, that if there would be, for example, 10 gravitational wave observation in the next year, and there will be 3 electromagnetic follow-up successful, everyone would build up models with electromagnetic emission in the merging masses. If there would be no electromagnetic observation, everyone would build up models without electromagnetic emission. And frankly, I think that everyone can create within a few days a model for both.
Science works. But actually, just one comment about this conspiracy of the detection. It has to be a conspiracy because the second event was detected at my birthday. So.
No,
sorry,
you know,
I need to cut this down because we are running a little bit late, so we can continue in the coffee break.
Just said this. I believe they are real observations. So what I'm saying is that there are really interesting papers occurring from very educated people working on the topic who are questioning the data analysis. And this is good because when the data analysis is good, it will be withstand such kind of investigation. If it is not good, in that case it is not worth to bother. So I mean it's important, you know.
Okay, let's thank Zsolt again.